All right, I think I'm live. Welcome everybody. Today we're going to take and how do I get my windows? So today on IAEI News Live, show all windows. There it is. All right, today I want to cover what we were going to cover last week, but we had a really good opportunity to interview and have a discussion with Susan Scearce, Susan Newman. And what was great about that opportunity was this is her final cycle, but she was chair of Code Making Panel 6, which speaks to the Ampacity discussion. So I want to dig into minimum rating and Ampacity, and I was wrong in some previous dialogues, and we're going to discover that together today on IAEI News Live. And it all starts now. All right. Okay, so we got Felix in the house. We've got Robert. Oh, here we go. Steve. And when upsizing, except for conductor conduit fill and temperature adjustment is equally important to comply with 251.2020. You know what? I've gotten a few emails about 251.22b, and we're probably going to get there. And I have an opinion on that. You know me, I have an opinion on just about everything. And if you don't have an opinion, I'll give you mine. So anyway, what I want to talk about is in 210 and 215, and I think 310 as well. I got to check. We have a requirement in 210.19. I'll use that as the example. And I should be able to move my water and come over here. All right, in 210.19, and hopefully you have your copy or your link to NFPA link open. I'm going to show you a few things that you may or may not have known about link, because we can open multiple windows, and I'm going to show you that as we go through this discussion. But in 210.19, if you recall, and I have it in my notes that I said, and somebody had made the comment, once you have minimum ampacity, you don't need to worry about size, because that will dictate the size. So we talked about possibly changing the title of 210.19 to just say minimum ampacity. And that would be 100% wrong, and I'm going to tell you why in a second here. And we're going to do some examples. But your journey in discovering when you need to, or how to select your conductor sizes and your ampacities and your corresponding overcurrent protected devices, you're probably going to begin in Article 210 or 215 or possibly Article 230. The low-hanging fruit from a awareness and knowledge perspective and ease of understanding is in 210 and 215, so we'll start there. Hey, Willie Snyder, happy Tech Tuesday. We got Nihad El Sharif and crew. We got Don Ganir. Good morning. Glad you're here, buddy. Good morning, Tom and everyone. And Felix Sandoval. So we've got South America or Central America. We got Colombia represented. Hello, and Laurel. We got research here and Dawn as well. Robert. Careful reading of all codes except the conditions of use, to name a few, as well as equipment connected location. Yes, and what Steve brought up was the 250.122b, and I have an opinion on that one because I can't understand why we have to do that, but hey, the code is what the code is, so we're going to follow those rules. All right, Willie Snyder, Vinny B., and and all. We got Eric Guadalupe. Hello and thanks for the insights, explanations, make better electricians. Absolutely, Eric. Thank you for joining in. And remember, Eric, from Puerto Rico, what we do here is not secret, right? So it's a train the trainer. So your job, as everybody else's job, including mine, is to try to share the knowledge as best we can throughout the industry. So, and then also when you disagree, speak up. That's what the comments are for. All right, so let's get back to this discussion, and I hope Puerto Rico is doing well. So 210.19 tells us we have two calculations in A. So 210.19, I have a hard time with 19, tells us branch circuit conductors for circuits not exceeding 1,000 volts AC, 1,500 volts DC shall be sized in accordance with A through D. A is your general requirement. That's where everybody goes in general, right? Because that's why they call it general. And then you have branch circuits with more than one receptacle in B, household ranges and cooking appliances in C. There's special requirements there. And then they have other loads like your individual lamp holders, luminaires with tapped conductors, individual outlets. And that's D. We're going to focus on A. So A, okay. I remember this comment. I can't remember where it came up, or I know it was on one of these programs because it was a chat. But we said, okay, minimum ampacity and size, and we can lose the size because we already have it with ampacity. And the reason that's not right is, and in fact, if I look back at some of my educational stuff, we end up picking up the right conductor. But I took the advice of somebody and I combined A1 and A2, picking a value of current and then going straight to a minimum size. That's not quite accurate and correct. And here's why. A1 tells us to focus on the equipment. This is continuous and non-continuous. 125% of the continuous plus the non-continuous. You do not consider conditions of use. And we had someone who commented, and I believe rightfully so, and we had, remember I told you during Code Panel 2, this cycle, we had somebody who wanted to remove the word ampacity because we're not talking about conditions of use in A1. It has nothing to do with ampacity at all. This has everything to do with the equipment and 80% rated equipment. So if I have 80% rated equipment, I know that I need to take 125% times the continuous plus the non-continuous, not the 125% of the non-continuous, just non-continuous. So I take, if I have 100 amps of continuous and 50 amps of non-continuous, I would take 100 times 1.25 and get 125 plus the 50 amps of non-continuous. So, and then I would add those together, and then I would go and find in Article 310 the size of conductor that would be adequate for that. But, and you'll notice in the parent text, which I couldn't understand before. I couldn't understand this. Now, this is all coming together. This is all coming together for me. You're probably sitting there saying, Tom, I've done this way, and I don't know why it took you this long to figure this out. But I'm a slow learner. So, what that 110.14c means in the parent text of A, and where you would use it, is in A1. What you do is you take 125% of the continuous plus the non-continuous, and then you go to table 310.16 and you select a conductor there based upon the equipment temperature rating. So, for example, let's just do an example of 108 amps. And what I'll do is I'll do 108 amps of continuous, and then we'll do another example of 108 amps of non-continuous. And you've probably seen my spreadsheet before. I'm just going to delete these. And we're going to do 108 amps of continuous, and let me share my screen. All right, so here's my load current. Let me take this out of here. There's my 108 amps, and this is the first part of our journey. This is going to determine the minimum conductor size. And I'm telling you, if you do it this way, you'll come up with the right conductor minimum size, and it'll be easier to pick the overcurrent protective device. So 108 amps of continuous load. If it's continuous, I have to take 125% of that, which means I get 135 amps. Let me do this. I'm going to come over here. Let me show you something while I'm doing this. So I'm going to come over here and I'm going to go to chapter 3. Now I'm in NFPA link here. I go to chapter 3. I go to article 310. And I go to 310.16, I right mouse click and open in a new tab. So now I have two instances of NFPA link open, one in table 310.16, and I can make as many tabs as I want. So if you want a little trick of the trade, this is a good one so that you can have a tab open for each of the sections, because you know as well as I do, we bounce around the code a lot. And I learned this too. Pin the header. That way, any way I scroll, the header stays the same. All right, so let's go back to my table. So I have 108 amps of continuous current. That means 125% of the continuous current is 135 amps. What I do then is I come to, and this is going to be 75 degrees C equipment. So that's going to be my limiting factor. I come to the 75 degrees C column, and I have to find something that is equal to or greater than 135 amps, which means it's a 1-aught conductor. If I go back to my spreadsheet, for copper, my sheet's telling me my minimum size is 1-aught because it's using the 75 degrees C column. If I use aluminum, I've got to move that to a 2-aught. And that's because in the 75 degrees C column for aluminum, a 2-aught gets me to 135 amps exactly. Okay, so there's my 135 amps right here. 135 amps in the 75 degrees C column for aluminum. 135 gets me a 2-aught conductor. Okay, so now I know that the minimum size based upon 125%, which has nothing to do with the conductor, it has everything to do with the equipment. I'm going to use table 310.16, ignore the insulation ratings. I'm going to go to my 75 degrees C column because that aligns with 110.14, and I'm going to pick a conductor size that is equal to or greater than this 125% number, which is 135 amps. And that would be a 1-aught conductor. Now, the second criteria that you find in 210.19, the second criteria, it says the minimum branch circuit conductor size shall have an ampacity not less than the maximum load to be served after the application of adjustment or correction factors. So now I'm dealing with the conductor only. I'm not dealing with the equipment at all. All right, so forget about the 75 degrees C column. Forget about 80%, all that jazz. I'm just dealing with the ampacity of the conductor based upon conditions of use, which is number of current carrying conductors in a raceway and the ambient temperature. So for our example, my conditions of use are going to be 3 conductors in a raceway and 86 degrees Fahrenheit. Now we can change these and see what happens, but let's start with something simple first. All right? And these conditions of use of 3 current carrying conductors in a raceway and 86 degrees Fahrenheit ambient aligns with table 310.16 conditions of use. So the ampacities found in that table for the insulation rating, which we're going to use 90 degrees C insulation, are accurate for this application. So for A2, I'm going to only worry about the conductor. The conditions of use, because it's 108 amps of continuous load, and my multiplying factors are unity, because I'm not adjusting the conditions of use, I need a conductor that has, based upon its insulation rating, an ampacity value of at least 108 amps. So I'm going to go to table 310.16. I'm going to use copper. We're using copper conductors, and I'll tell you what both copper and aluminum, but we're going to use the example of copper. And I have a 90 degrees C insulation, so I'm going to use the column for 90 degrees C. And I'm going to scroll down until I find a number that is greater than or equal to 108, which is this 3-gauge conductor, which is good for 115 amps. So that tells me that based upon the conditions of use, the minimum conductor size is a 3-gauge, which is what I have here. For copper. For aluminum, I am up to I'm up to a 1. Why? I don't know why I have a 1 in here. I gotta check my D. For some reason, oh, I know why, K2. I gotta go to K2. K. So there's my 1. I wanna make sure this is a K2, yep. So I have the wrong column. So my minimum size conductor, Control C, I need to copy this all the way down, Control V. My minimum conductor size for this application is a 1 gauge, which aligns with the 90 degrees C column for copper conductor insulated based upon 310.16. That would be this column right here. Hopefully you can see my mouse. I'm not sure if you can. Right there, I highlighted it. Okay, so I have the 90 degrees C column. I've got a 1 gauge. 115 amps is the next one above 108 amps. Okay, so my minimum conductor sizes for copper, we'll just use copper. I have the choice of 2. I have a 3 gauge or a 1-aught. And the larger of the 2 is the one that I pick. The larger of the 2 for the minimum branch circuit is going to be a 1-aught conductor. So that takes care of 210.19a. The first step in this journey was to determine the minimum ampacity, and the reason that it says minimum size is because A1 has nothing to do with ampacity. It has just everything to do with the size of the conductor for the equipment because of 110.14. Eric Guadalupe, according with your oh yes, for aluminum, good point. Aluminum, for this application, your You have two choices, right? So the minimum size based upon 125% is a 2 watt. The minimum size for the just based upon ampacity is a 1 gauge. The larger of the two is what you pick because 210.19 says branch circuit conductors shall have an ampacity not less than the larger of the following and comply with 110.14c for equipment terminations. So the larger of the two is going to be the 1-aught conductor or 2-aught conductor for aluminum. That is 2-aught handles, what is the 2-aught? A 2-aught conductor based upon the 75 degrees C is 135 amps. Whoa, wait a second, 135 amps, do I got the right one? Oh yeah, 135 amps, because it's my 125% is 135 amps. So I need 135 amps worth of copper or aluminum conductor, and to get that, I need a 1-aught conductor. Based on the 75 degrees C, I need a 2-aught conductor. I'm looking at the wrong column. All right. Let's go back, because I probably just confused everybody. You do the two calculations. I determined the minimum conductor size for copper and aluminum based upon 125% of the continuous plus the non-continuous. I determined the minimum size copper and aluminum based upon the ampacity. The larger of the two is the one I pick. For copper, the larger of the two between a 3 gauge and a 1-aught, the larger of the two is the 1-aught for copper. For aluminum, I have a 1 gauge or a 2-aught. The larger of the two is the 2-aught. So if I have an aluminum application, the minimum size conductor has to be a 2-aught. If I have a copper conductor installation, then my minimum size is a 1-aught. But in your case in Puerto Rico, we are required bonuses copper wire all the time. So, but in your case, Eric, in Puerto Rico, we are required copper wire all the time. So if you're using copper all the time, then yes, your minimum conductor size would be a 1-aught copper. Perfectly fine. And that is your preference, that's your choice. And if you have a local law that states it has to be copper, then you're good with a 1-aught. If you are a design engineering firm and you say, look, this is all we're going to use is copper conductors, 1-aught. Regardless, it's a 1-aught. All right, so that's your minimum size. So now I need to protect. So now for 108 amps, for 135 amps, you know, based upon 240, I think, or no, is it 215? In Article 210, for overcurrent protection, 210.20 is going to tell you that your branch circuit overcurrent protective device has to be at least 125% times the continuous plus the non-continuous. So in our case, and that's in 210.20a, in our case, our minimum branch circuit conductor size is 135 amps. It can go larger. No. Yes, it can go larger, but it can't go smaller. But I have that criteria in my spreadsheet a little later. So we know what we're going to do is we're going to pick, for this case for copper, we're going to pick a 1-aught conductor. So I'm going to come here and I'm going to pick my 1-aught copper conductor. There's my temperature ratings, 75. There's my insulation rating, 90 degrees. My equipment, based upon, now this is a 110.14 requirement, my overcurrent protective device can't exceed 150 amps. I have 135 amps of continuous load. I can't be less than that. So 125% must be greater than or equal to a 150 amp breaker, because I don't have a breaker at 135 amps. my next largest overcurrent device for the 135 amps of continuous current, because I can't go less, is 150 amps. My equipment, I have to be less than or equal to 150 amps. So far, 150 amp breaker is looking really good. I have to be less than or equal to 150 amp circuit breaker. And my ampacity is 170 amps based upon contingent conditions of use for this 90 degree C 1-aught conductor. If I look at the 90 degree C column on table 310.16, I'm going to see that my 1-aught conductor is 170 amps. So my ampacity is 170. The next larger overcurrent device, because I'm permitted to go to the next larger overcurrent protective device for the ampacity of the conductor, is 175 amps, which is my standard overcurrent protective device size. All right? So I'm going to pick a 150 amp circuit breaker because it is greater than or equal to the 135 continuous. It is less than or equal to the equipment, that's the 75 degree C column, which is 150 amps. And it is less than or equal to the next larger overcurrent protective device from the ampacity of the conductor. So a 150 amp breaker is going to protect the conductor, it's going to protect the termination, and it's large enough so that the continuous current doesn't exceed the rating of the overcurrent protective device. My conductor size is a 1-aught, it is a copper, and then I do my comparisons. I'm okay on the next larger than ampacity, I'm okay on the equipment protection, and I'm equal to or over or greater than the 125%. And I'm not less than the load current. So a 150 amp breaker would be appropriate for this application. All right, so Eric, now what I'm going to do is I'm going to say, let's take this same continuous current and we're going to make this a non-continuous load. So I'm going to put it into 108 amps, following the same journey that we just did, going through 210, moving over to 110.14 or 110.14 for terminations, and then 310.16, all that jazz. My total load is 108 amps. My 125% number, the 125% times the continuous plus the non-continuous, is still 108 amps. My smallest conductor size is a 2 gauge for copper. My smallest conductor size for aluminum is a 1-aught. If I look at the conditions of use, I have 3 conductors in my raceway, 86 degrees Fahrenheit, so unity on conditions. That means, based on conditions of use, my conductor has to be able to handle 108 amps. Based on conditions of use, I can pick a 3 gauge copper or a 1 gauge aluminum. So my choices in copper is a choice between 3 and a 2. The larger of the two is the 2 gauge because, you know, as the numbers get smaller, the conductor gets larger. So I go from my size conductor is a 2 gauge. My terminations are still going to be 75 degrees C. My conductor insulation is 90 degrees C. My equipment, based upon that size conductor, my overcurrent device can't exceed 115 amps. My ampacity is 130 amps. I can go to the next higher if it's not equal to a standard ampere rating. So, knowing that I can't exceed 115, my equipment, I can't be greater than 110 amp overcurrent protected device. So my overcurrent protected device has to be 110 or less. My overcurrent protected device has to be greater than or equal to 110. My ampacity of the next larger is 150. So if I pick a 110 amp breaker to protect a number 2 gauge. Do I got that right? Yep, number 2. If I have a 110 amp breaker to protect a 2 gauge, I am good on ampacity. I'm good with equipment. I don't have a continuous load, so I don't have to worry about being greater than 125%. I just have to be greater than the load current, which is fine. I get a yes. So a 110 amp circuit breaker would work perfectly fine for this application with 108 amps of a non-continuous load. I meet all the rules. I'm protecting the equipment. I'm protecting the conductor, because the conductor's ampacity is 130 amps, and a 110 amp breaker is going to protect the conductor at its ampacity. Now, could I put a larger conductor size? Could I go to 125? No, I can't. If I go to 125 amps, the next larger size, now I'm not protecting the equipment. So I'm going, my equipment, I'm exceeding the 110 amps, which is based on the 75 degree C column. And you wouldn't go there anyway. Why? Because you'd be buying a larger overcurrent protective device than what you need. And who wants to, well, wait a second. If you want to send money my way, please do. But if you don't need to, you don't have to. All right, so now let's take the same 2 scenarios. I'm going to copy these, and we're going to change the conditions of use. We're going to leave 3 raceway conductors in a raceway, but we're going to take the ambient. Let's say, for example, a good length of this is in the attic, and it's 140 degrees Fahrenheit. I use Fahrenheit because I don't know Celsius. I'd have to do a conversion somewhere. So I'm just doing the conversion for you. 140 degrees Fahrenheit. That means my multiplier on ampacity, I heard it click. Laurel says, nice spreadsheet, well done, logic. Oh, yes. Yes, that's right. I have to put the code references. Laurel, you said that once before. I'm going, and here's the other thing I have to do with this spreadsheet, Laurel. Let me walk through this and I'll tell you where I need to automate something. Right now it's a manual process. And I just added a couple columns in there. So what I just changed was the ambient temperature. So the first step, 125%, is exactly the same. For 108 amps of continuous, it's 135. For 108 amps of non-continuous, it's 108. Piece of cake. My largest conductor size based upon that, which has nothing to do with ampacity. It has everything to do with the equipment based on the 75 degree C column, is 1 aught for the 108 of continuous and a 2 gauge for the non-continuous. And I'm just going to talk copper for now. Now we get to the conditions of use. 3 conductors, it's unity, elevated ambient temperature, 0.71. So now my conditions of use, my ampacity has to be greater than or equal to 152.11. To get that done in copper, a 1 aught will satisfy both conditions. So the larger of the 2, let's start with 108 amps of continuous. I have a 1 aught conductor and I have a 1 aught conductor. So I'm going to stick with a 1 aught conductor, which is exactly what I had before. For the non-continuous, I have a 1 aught conductor for the A2, and I have a 1 aught conductor for the conditions for the 125%. So in both cases, I'm into a 1 aught conductor, whether it is 108 amps of continuous load or 108 amps of non-continuous load. Regardless, I'm using the same size conductor. And hopefully you see how I got there. I did the 2 evaluations, and they both resulted in a 1 aught conductor, 1 aught copper. All right. So 75 degrees C, 90 degrees C insulation. So now, here's my criteria. For the continuous current, I have 150 amps. My overcurrent device has to be at least 150 amp breaker to be greater than or equal to the 125% number. Why is that? What's the continuous current? 135 amps. I can't be less. I go to the next larger size from 135, and that would be 150 amp breaker. So, and that's the same as it was before. So I'm going to pick 150 here. For this one, 110 amp breaker would satisfy the 125% rule, but because of the size of conductor and the ampacity, I can't be greater than, so I can pick 110 amp breaker here too, because 110 amp breaker would be greater than or equal to the 110 amps, which is the 125%. The 110 amp breaker would be less than or equal to the 150 amps worth of equipment for the termination. And the 110 amp breaker would protect the conductor at its ampacity because it's 120.7. So I'm going to say 110 amp. I have the same conductor size for both, but for the non-continuous load, I can use a smaller circuit breaker size, which satisfies all of the conditions. So that's the basic difference between 108 amps worth of continuous versus 108 amps worth of non-continuous. The conductor size minimum conductor size is still going to be a 1/0 because of our 210 selections, minimum conductor, size, and ampacity. But my overcurrent protective device is able to be smaller, exactly 2 sizes smaller. I can put, now let's take a look at, I'm just worried about the UL standard. Let's take a look at the UL 489 standard while I call this up. I'm going to grab the UL 489 standard. Where's it at? I go to Documents, I go to Organizations, I go to UL, I go to 489, and here it is. Okay. All right, let me click on this. How do I do this? All right, so, hey Lou, you may be late, but you're worth the wait. And hey Lou, you know what? You're painting the garage. Guess what I'm going to be doing right after this? I'm going to put a second coat. Bobby Joe and I are going to put a second coat on paint on the floor. So we redid our floor. I ground the floor down using a grinder along the entire garage floor. We cleaned it multiple times, hosed it, used acetone or whatever you call that stuff that evaporates real quick. Cleaned it. Then yesterday we painted it with the first coat. We used U-Coat It is the name of the manufacturer that we used. You used a U-Coat It. And today we're putting the second coat on, and tomorrow we're going to put the clear, the poly, I guess you want to call it. Ugh. All right, so I'm going to go to UL 489, and just to refresh your memory, we have a 110 amp breaker on a 1/0 conductor, a 110 amp breaker on a 2-gauge conductor, 150 amp breaker on a 1/0 conductor. Hold on, what's this say? It says, oh boy, wait a second. Oh, I can't use 150. I got to use 125. 150 amps for 108. I can't use 150. I've got to use 125 because of the ampacity. Boy, good thing I checked. But 125 is not over. Oh boy, wait a second. I'm going back. Let's go back. Let's go back. Hold on, guys and gals. I have 108 amps. I'm going to look at this one right here. Let me highlight this puppy. 108 amps worth of continuous. My minimum size is a 1/0 for the termination. My minimum size for conditions of use is a 1/0. I pick a 1/0. The ampacity is 120, so I can go to the next larger, which would be 125 amps. So if I pick 125 to protect a 1/0 copper, I'm not over 125%. So I need to increase the conductor size. I need to increase the conductor size. Let's pick this up to a 2/0. If I move that up to a 2/0, now I can have 175. I can put 150 on there now. 150. There it is. Now I've met all my criteria. So I was not protecting the conductor at its ampacity when I was using a 1/0. So in this case, for 108 amps of continuous current, because of the ampacity adjustments, I had to increase the conductor size based on conditions of use. The minimum circuit size based upon those previous two evaluations, which led me into a 1/0 conductor, was not adequate enough because my overcurrent protective device, let's go back and let's do that again. Let's take it back to a 1/0 to explain why. My ampacity of a 1/0 is 120.7. My overcurrent protective device would have to be at least 125 amps or less, maximum of 125 amps. I could be less than 125 amps, but I can't be greater than 125 amps. My 125% rule puts me into a 150 amp breaker. 125 amps, 125% is 135 amps, remember. So my overcurrent protective device can't be less than 135 amps because of the rule in 210 that tells me my overcurrent device has to be greater than 135% of the continuous. So 125 amp overcurrent device isn't going to work. I pick 150, and I had to increase the conductor size because of this right here. I have to go from a 1/0 to a 2/0. I increase this to a 2/0. That brings the numbers for the conductor up. The ampacity is now 138.45 because I multiply the table by the conditions of use. The overcurrent device has to still be greater than 150 amps, but my ampacity value now is less than or equal to 150, so I can put a 150 amp breaker on it, and I'm still less than the equipment rating of 175, and I meet all my criteria. So now, okay, so now we have that ironed out. Now we're going to go to UL 489, and let's take a look at the table in UL 489 for a 110 and 150 amp breaker, and make sure that our selection aligns with how we test overcurrent devices. So what we've got here, let me do this. All right, so I have a 150 amp breaker with a 2/0, a 110 amp breaker with a 1/0, a 110 amp breaker with a number 2, and let's bring this table over. And this is in UL 489. And this is table 6.1. I don't want it to do that. 50, 60, 70. I need 150 and 110 amp. there's 110 amp, and we test that with a number 2. You see that at the bottom? 110 amp breaker is tested with a 2 gauge. So there's my 110 amp breaker tested with a 2 gauge. 110 amp breaker with a 1/0, that's a larger conductor. I can always go larger than a 2 gauge as long as the lugs will let me do that, because a larger conductor is going to wick off more heat. So the smallest I can go with a 110 amp breaker is a 2 gauge. And a 150 amp breaker is a 1/0. So the smallest conductor I can use on a 150 amp breaker is a 1/0. So there is 150 amp with a 2/0. That's perfectly fine. I can go larger than a 1/0. Wicks off more heat. There's 150 amp. There's 150 amp with a 1/0 conductor, and that's perfectly fine because a 1/0 copper conductor is the smallest conductor that I can put on that breaker. All right, so Lou Petrucci, whatever. I can never say your last name right. Anyway, what we just did was we went into 210, Article 210, and we followed the process in 210.20. And here's what I learned. Here's what I learned. That in 210.19, when we talk about minimum ampacity and size, both of those terms, ampacity and size, are accurate and correct. And the reason is because in 210.19a2, we're dealing with the ampacity based upon conditions of use. And in 210.19a1, we're dealing with equipment, and it has nothing to do with ampacity. It's just based upon the equipment temperature rating and the size of the conductor that has to get you to, based upon the temperature, say it's a 75 degrees C or a 60 degrees C or 90, whatever column aligns with the equipment, which is the lowest temperature rating on, remember, every conductor has 2 sides. So I've got to look at the temperature rating on both sides, whichever one has the lower temperature rating. That's the column I'm going to use on table 310.16, because that aligns up with 110.14. And in A1, I'm picking my conductor size simply based upon the termination. Separate this into 2 actions. One is the equipment, the other is the ampacity. When it comes to the ampacity of the conductor, Article 240 tells me I can protect that conductor by going to the next larger. When it deals with the termination, I can't go greater than what's in the 75 degrees C or 60 degrees C or 90 degrees C, whatever the temperature rating of the termination or the equipment is. I can't exceed that value in my overcurrent protective device. Conductor ampacity, next larger. Overcurrent protective device from the ampacity of the conductor. 110.14, equipment, temperature rating, I can't exceed the temperature ampere value based upon the temperature rating of that termination. And we just did it in 210. Now, 210.19, if I go to Article 215, I'm going to find a similar section, which this says minimum rating and size. In 215, this should say minimum ampacity and size, because we went through this a couple cycles ago. Conductors do not have an ampere rating. They have an ampacity, period. There is no such thing as an ampere rating for a conductor. So it should be minimum ampacity and size, and 215 should align with 210. And we can get that done on panel 10 this next code cycle. But you're going to see 215.2A1 and A2 are the same two type of calculations that we just did for a branch circuit. So regardless of whether or not this is a branch circuit or a feeder, I have the same process. The difference is going to be how I determine the load current. If I have a branch circuit feeding HVAC, feeding a motor, feeding an oven, any type of specific loads. Now, outside of, if I have a branch circuit that's feeding, 14 receptacles, that's a little different on how I handle that. But the branch circuit, I'm going to determine the load based upon what that branch circuit is serving. Feeders serve multiple branch circuits. So there's probably a little bit more work that has to go into determining all of the loads on a feeder that are continuous and all of the loads on that feeder that are non-continuous. All right, but it's the same process. 215.2, you have your continuous current loads, and you have your ampacity and adjustment corrected factors. And this was the word that during this past cycle, shall have an ampacity, and that's wrong. That's not right. And hopefully we can fix that this cycle. That should not say ampacity. And then let's take a look at 230. Now 230 is a little different. 230, you have your general requirements, you have your overhead service conductors, your underground service conductors. Let's talk about Steve. What's Steve got to say? The portion of the conductor that terminates on the breaker can be spliced to comply, so the breaker terminal limitation is not absolute. The portion of the conductor that terminates on the breaker can be a splice. A portion of the conductor that terminates can be a splice. I think what you're saying, Steve, I believe, and correct me if I'm wrong, I believe what you're saying is that you can come off of the breaker and then land, say, on a 90 C lug in 90 C equipment and go from 90 C to another 90 C. So that portion of the conductor on the other side of that splice that's in between two 90 C pieces of equipment, I can have at a different temperature rating. And I would agree with that. I'm not sure what you mean. I think that's what you mean. The portion of the conductor that terminates on the breaker can be a splice. I'm not sure what that means. The challenge you have, like on a 150 amp breaker, I'm not going to put two different conductors under the same lug. Right? So now if you splice the conductor, a larger or smaller size than the terminals are labeled for. Yeah, as long as you're protecting the conductor at its ampacity. So what I don't know if I can do this. Let me see if I can do this. Let me see if I can do this. Hold on. Me and iPad not getting along. I'm not seeing it. Give me 1 second, Lou. Let me see if I can do this. I'm going to try something. Or Steve, I'm sorry. I'm going to call you Lou. I'm trying something. And shizza no work. Me iPad over. Me iPad green. Me iPad Eugene. It's not working. I don't know why it's not working. I don't know why. Whoa. Replace asset. Cancel. I was going to try something, Lou or Steve. New camera. I'm just still trying something. Hold on. It's not working. I don't know what I did. I don't know how to do this. I don't know why it's not working, but it's not working. But what you're talking about is coming off the breaker with a smaller conductor, go to, or off with a larger conductor, go to a smaller conductor, use it at its 90 degrees C ampacity, because now you're at 90 degrees C, because you're no longer limited by the overcurrent device. I agree with you 100%. And honestly, you don't need a code permission to do that, but we added it in 210 and 215. You don't need a code permission for that, but we added it, so not a big deal. And I'm not sure why my conductor is not working. But anyway, my conductor, my iPad wasn't working. All right, so great point, Steve, and I'm glad you brought that out, because that is a very important piece of the puzzle. Yes, Robert, you have to do the larger of A or B, but here's what Steve is saying. I don't know if I have. I might here. You know what? I'm going to do this. I'm going to draw what Steve is talking about. Okay, so let's do this. New. How much time I got? Okay, we got a couple minutes. So what he's talking about, delete. Let's say I come off and I come into equipment, Control Shift back. Boom. All right, and I have a terminal block in here. I am just going to draw this just for giggles. Okay, Control Shift front, and I land there, and then let's say that I do this. I'm going to duplicate that, Shift, and I do that. And I'm going to copy this, Shift, boom, Control Shift back. And let's say that I do this. Okay. I'm going to move this over this way. And I'm bringing this over this way. I might have to move this over a little bit like that. That. Shift. Nope. Alt. There we go. All right, so let's say, for example, that I have 75 degrees C equipment here, 75 degrees C equipment here. I come off of this breaker and I land on say a terminal block, a piece of equipment that's rated 90 degrees C with a terminal block in there, and then I come from that 90 degrees C to this 90 degrees C. So now this conductor, boom, right here, wait, and I need to put an arrow. I need to put an arrow on the end. That conductor and I'm going to say conductor used at its 90 degrees C rating, 90 degrees C ampacity values, right? So now I can use and size that conductor based off the 90 degrees C because now my equipment on both ends is 90 degrees C. I can put a smaller conductor in that application for that distance between those two pieces of equipment. And that could save you a lot of money doing it that way. All right. See my comment right before Robert's. Correct. The size ampacity shall be protected, but an upsized 8 gauge can be spliced to a 10 gauge to fit the 20 amp breaker terminal. Depends on the conditions of use, I know that. And what you're doing is you're basically an increased size. So you want to go to a size larger conductor. Okay, so you're going to a larger conductor, not a smaller conductor, so that you can put that into the 20 amp circuit breaker terminal. Yeah, you can do that. You're perfectly fine because you've gone to a larger conductor, even if it's used at 75 degrees C. So what you're doing is this. You're doing, take this out, and let's turn this into, I don't know what we'll turn that into. And we'll call that like a wire nut or whatever you want to call it. Right, a splice, and you're saying that this conductor, larger 8 AWG conductor, and you're saying smaller, 10 AWG conductor. So that's what you're doing. Oh, I lost my arrow. Shift. That's what you're saying. And I don't have a problem with that as long as this method can handle both size conductors. And it's listed for that. So those wire nuts might be able to handle that. I don't know. But that's not a bad idea. I like it. Don Gannier says, if there's much load on the 90 degree C conductor, it runs most of the time. I'm not going to permit that if I'm paying the power bill. A long-term power cost will exceed the installation savings. And that would be outside of the code. And that would be your... that'd be your right to do that. It's up to you. That would be a design decision, and I can't disagree. And what Don is getting to is the fact that the smaller conductor is going to have a larger impedance, right? So that will cause I squared R losses. So I've never done the math to know how much, like if I decrease the size of the conductor and I'm using it continuously, what's the dollars does that translate into? I don't know what that answer is, what the additional heat loss. I don't know if it's significant enough because eventually that conductor's size and the savings will be translated possibly into a higher energy bill, but I don't know what your return on investment is going to be. When is the break even? It could be 100 years, it could be a year, it could be 12 hours. I don't know. Dawn, if you've done any homework in that regard, where you know the price difference between the two, and then based upon the energy rate, that'd be an interesting little piece of info. But good point. 230.42, same process except for 100% rated. Yes, definitely concerned as that's a consequence, especially with larger systems, Dawn. Yep. Willie says, I'm wiring a large commercial building, and for some reason the electrical engineer has a number 6 gauge copper with a 10 for an AHJ with a 10. I'm not sure what that means. If he routed them in the same raceway, that's minimum circuit capacity, a 6 gauge copper with a number 10 for an AHU. Air handling unit. A 6 gauge copper with a number 10. I'm not sure what that means. 32 amps. That's one case where I think 250-122B makes sense. I'm not sure what you mean by a 6 copper with a 10. I'm not sure what that means. A discussion for another show. Yes, I agree. Yippee. Andrew Casney. Good to see you, buddy. Picture a overhead service drop. Excellent. Good to see you here, Andrew. True, however, code doesn't care if it is efficient or cost effective. That's exactly right. Most installers care about cost to install, not operate efficiently. That's true, Robert. Steve, yes, larger or smaller splices to the breaker as long as everything else complies. Absolutely. Thank you, Laurel, very much. Thank you for all you do for the electrical industry. And Dawn Gannier says, of course, that is what the contractor installer is concerned about, but that is not in the best interest of the client. I often upsize industrial motor circuits one size to save the client money. Yep. I'd love to see the math on that one, though. I really would, Dawn. That would be a great program. Steve says, if you're upsizing, Dawn, you're in 250-122B for the ground, which I don't understand why. It doesn't make sense to me. Anyway, I did the math. To upsize motor circuit wires, one size for industrial motors, if the raceway did not have to be increased, the payback was 3 to 5 years, but only for motors that run most of the time. Good. Thank you, Dawn. I knew you would do the math. I knew you did that. And Willie is saying a number 10 EGC. And Lou, thank you very much, Lou. I appreciate the feedback. And I hope everybody got something out of today's Tech Tuesday. And I'm glad we had an opportunity last week to sit with Susan. If you did not have a chance to watch that program with Susan, I hope you go back and take a look at it. We had a really nice discussion. She's a great person, and she was there at the Standards Council for the hearings for the appeals, and the results of which I'm not sure when those are going to come out, but I'll look forward to seeing those. So anyway, go back and take a look at that one. I hope everybody got something out of today's discussion. And I'm going to run in and do something in the garage. Got to paint the floor. All right. Thanks, everybody. Jerry O'Connor, thank you for joining in. And we were just on a phone call, and Jerry was like, "Oh, you got to go." It was 1 minute too. So I appreciate you dialing in, Jerry. All right, everybody, take care, stay safe, and please stay healthy. I'm out of here. Got to go get some work done. See you next week.